Yes.
Yes. So we now can see our today's speaker. It's my great pleasure to have Franco Nori with us. Thank you, Franco, so much for your agreement, for agreeing to deliver this lecture on quantum optics with giant atoms. You are welcome at our Kharkiv quantum seminar. And I would like to introduce Dr. Nori in 2 slides. One is more or less official, and another less official, more scientific. Franco Nori is the Rekin chief scientist. He leads theoretical quantum physics laboratory, and also he is a team leader in quantum information theory research team in the Rekin Quantum Computing Center. Also, he has a concurrent position at the University of Michigan. Franco received his PhD in physics from University of Illinois, and then he was a postdoc at the University of California in Santa Barbara. Then he joined the University of Michigan, and for more than 10 years, for how many? For 23 years, Franco is in RIKEN, right?
Yeah, yeah. Mm.
RIKEN is the Institute of Physics and Chemistry, somewhat analogous to our Ukrainian Academy of Sciences. The group of Dr. Nori has done and continues to do pioneering interdisciplinary studies at the interface between different areas of physics: quantum optics, quantum electronics, nanoscience, photonics, condensed matter physics, etc. Dr. Nori has received numerous awards and prizes and medals, and several medals, and very recently he was awarded the Charles Hart Towns Medal. And when it is given to you, Franco?
Sorry?
When is it given to you, the medal?
It would be May in a few weeks in the United States. So I need to fly there.
Exactly. So it's very recently. He is an elected member of 3 Academies of Sciences and also an elected fellow of several physics societies. Franco Nori has been listed by the Web of Science as a highly cited researcher in physics. This means that he is among those 0.1% of physicists which are selected for this title. About the works in his group, I would like to tell in one slide by quoting several wordings from the papers of him and colleagues. This was not discussed with the speaker. Quantum biology, quantum simulation, quantum metamaterials, quantum football, the title of the paper, how to test the quantumness of a quantum computer. 1 photon can simultaneously excite 2 or more atoms, which is exactly the title of one of the letters. Optimization of lattice surgery is hard. Mirror, it's one of the papers with our participation on the LZSM interferometry. Domino cooling, Pokemon, diagnosing quantum chaos, and many other works related to, in particular, to quantum physics. So with this introduction, Franco, I would like to give the microphone to you. The floor is yours, please.
Okay, thank you for the introduction. Do you see now one slide or 2?
Yes, 1 in the full screen mode.
Okay, let me go into the pointer here, laser point. And you see the laser pointer?
Yes.
Okay. Thanks for the kind introduction. I would like to talk about giant atoms, a new frontier in quantum optics. And as you can see here, there is a cartoon of an atom, a red one, interacting with a blue one, but instead of interacting through the usual, let's say, electromagnetic interactions, this red atom will be replaced by an atom on a chip, which is this one here. And then the blue one with an atom on a chip here, and they will be talking via these coplanar waveguides, which confine the electromagnetic field along these essentially one-dimensional objects. The Z component essentially negligible. The transverse component is negligible. It's all longitudinal. So essentially, it's like a 1D coplanar waveguides essentially allows the atom here to interact here with this qubit, and then here with this qubit here, and then with this artificial atom here, and then back there. So let me see if I can get to the next slide here. Oh, this is haiku. This is a short Japanese poem. And then let me see if I can get the slide here. Superconducting circuits with Josephson junction qubits can behave like artificial atoms on a chip. So this is a summary of the main idea that we want these circuits to behave like atoms that you can design on a chip. You can design how they interact with each other. So this could be seen as exactly this is quantum optics using giant atoms. So superconducting circuits can simulate or emulate atoms and can be used as quantum simulators. My understanding, there are students in the audience, so therefore, if students are interested, there are two popular reviews online, one with a postdoc of mine on quantum simulations, a very short review in Science published some time ago. There are almost no questions, it's mostly pictures, it's very easy to read, it's like a Scientific American paper, almost like so this is non-technical at all. Then for the people who want to see more detail, there is a very long review on reviews of modern physics on quantum simulation. And at these, many students have found this to be useful introductions to the field. There are also pedagogical broad overviews related to artificial atoms for quantum information. There is a very pedagogical, non-technical one for non-experts on quantum technologies, like 2 pages in Physics World. There is a slightly longer one focusing on the experimental and physics aspects of natural and artificial atoms for quantum computing. This is an overview covering many different kinds of qubits, not just superconducting, but also semiconducting and NMR and photons and all the other ones. Regarding superconducting circuit, there is a popular review that students and postdocs and non-specialists find it useful. It is in our website, so you can get them for free, all of this. There is even a special page devoted to reviews, and this is Physics Today, has been translated in different languages. There is a longer one, Atomic Physics and Quantum Optics use superconducting circuit, because there is the misconception that the circuits can only be useful, if anything at all, for quantum computing. This is false. Most of our studies is about atomic physics and quantum optics, using the circuits as artificial atoms. So this is the goal. And this is a pedagogical 11-page review with a postdoc, former postdoc of mine on in Nature. This one is also available on our website. So students in the audience who would like to see background on an expert, there is a comprehensive review on microwave photonics with superconducting quantum circuits, also on our website, and a very pedagogical introduction on quantum bits with Josephson junctions in a book chapter, which is also available on our website. So there is they are all easy to access. There you type my last name, Rick, in publications, you can get them all. Now, a brief summary of the talk. In quantum optics, atoms are usually approximated as point-like. Compared to what? Compared to the wavelength of the light they interact with. However, recent advances in experiments with artificial atoms built from superconducting circuits have shown this assumption can be violated. And there are several papers on this. This started actually in Chalmers, Sweden, where they pioneered this work. And then one of the pioneers of this work joined my group for 4 or so years, and then we're still working together, Anton Fries Kokkum. And then instead, these artificial atoms can couple to an electromagnetic field in a waveguide at multiple points, which are spaced several or many wavelength distances apart. These systems are called giant atoms. I will show you several diagrams in a moment. They have attracted increasing interest in the past few years, and there is a review by Anton Fries Kokkum. It's an excellent review by a leader in this field and one of the pioneers in this fantastic, exciting area. In particular, the interference effects due to multiple coupling points allow giant atoms to interact with each other, to talk to each other through the waveguide without losing energy into the waveguide. So I will briefly review some of these developments. And we have also shown that this giant atom coupled to waveguide with different impedance can give rise to chiral bound states. So I'm going to focus mostly on results obtained with Anton Fries Kokkum and Göran Johansson, the advisor there in Sweden, and myself, that was like years ago. Then the experiments were done at MIT in 2020, but we had new results 2021, 2020. The past few years, even now we're getting more results, but these are more technical, so I'll focus in on these ones here, because in this case, there are theory experiments. In the other ones, the more recent one, we have only theory. The experiments are in progress. So there are more recent results. The main message of this talk has been already summarized. So why? Because most people fall asleep after the first few slides. So I just want to make sure that you will all see the slides at the beginning. So let me start with an introduction about atom sizes and their history, very briefly. Then one giant atom. Hello? Oh, I think somebody might need to turn off the, okay, great. Turn off the microphone there.
Now it's all right.
One giant atom, we are going to see that it has a frequency-dependent relaxation rate that can be controlled and tuned. Then what happens when you have multiple giant atoms? And is it possible to have them interacting in a way which is decoherence-free? This at first sounds impossible. Every time the atom is interacting with the environment, you get decoherence. So therefore here, if you choose the parameters properly in this control environment, which is the circuit on a chip, then it is possible to do it theoretically and experimentally. Then we have other results on chiral quantum multi-generation, which I will not describe now because it's a bit more technical, but if people are interested after the talk, I'd be glad to show a few more slides, but they're more on the technical side. We have more recent results, which I will not show today, and then a summary. So let's start with the atom sizes and their history. The interaction between light and matter at the level of photons and atoms has been studied for a long time. The coupling light-matter is very weak. So Serge Haroche, Jean-Michel Raymond, Michel Brun, and others, they were struggling for a long time on increasing the coupling between light and matter. And the coupling is very weak. Why? Because the dipole of the atom is very small. The charge is small, the distance is small, the electric dipole is small. So one way to change this is to elongate the atom. So you take the atom and you try to make it longer so it looks more like an antenna. So if the atom looks like an antenna, then the coupling to electromagnetic field is higher. So you get higher light-matter coupling. And this was a difficult problem for a long time. And that's why Haroche got the Nobel Prize about some years ago on cavity QED. Because the interaction between light and matter allows you to unveil very interesting, exciting physics. So many people have been working. So the question is everything already solved? Or there are new directions of research opening up, which is what this talk is all about. So because many things are understood, but it is possible to actually extend into new directions. So the size of an atom is usually small compared to what? Compared to the wavelength of the light interacts with. So you have a cavity, you have a wavelength of some electromagnetic field. So these are the two length scales, atom and the wavelength. The wavelength, there's nothing else there. The dipole approximation assumes the atom as point-like, neglecting spatial variation in the electromagnetic field. So we have small atoms, which are composed of atoms interacting with optical light, or Rydberg atoms interacting with micro. Rydberg atoms would be the hydrogen atom. You drive it to large N, and the main quantum number between 50 and 100. And then the Rydberg atom interact with microwaves. And then there are also quantum dots inside photonic crystal waveguides and also superconducting qubits. So there is a variety of these atoms, but as you can see here at the numbers here, if you look at the, I need to look at the pointer here, pointer options here. The pointer is not working here. Here it is. Oh, there it is. If you look at the numbers here, the ratio is very small, like 1 part in 10 to the 3, 10 to the 4. So therefore, the atoms are very, very tiny compared to wavelength of light. In the case of Rydberg atoms, they are always described as being large, but they are large compared to normal atom, but they are not large compared to macro. Macros are typically 1 centimeter wavelengths, so it's within this range. So the ratio is actually 1 part in 10 to the 4, 10 to the 7. So the ratio is really tiny. This is taken from Harosh Nobel lectures, in which he was able to get a stronger coupling by elongating these atoms, making them more like an antenna. So, but the relative ratio, which is what matters in the cavity, you have the atom and the wavelength is very tiny. The same for the quantum dots in photonic crystal waveguides. So the photonic crystal is right here, the waveguide is here, there is here a quantum dot. The numbers are 1 part 10 to the 2. In the case of superconducting circuits, it varies 1 part 10 to the 4 to comparable. So you can have them medium size, let's say, or reasonably large. And so this is what people have been doing for a long time in this mostly last century and mostly this century, the ones at the bottom. The giant atoms are atoms that couple to the electromagnetic field at multiple points, which can be wavelengths apart. So let's consider a quantum harmonic oscillator. So you can get your inductor, your capacitor, and then when you get here, the energy levels are equally spaced. So this is your circuit here, quantized. This is not ideal if you would like to control it, because you put microwaves here, and you're exciting between 0 and 1, 1, 2, 2, 3, 3, 4. Essentially, they're all equal energy. There is no fingerprint for each transition. If you replace the inductor by a Josephson junction, which can be seen as a nonlinear inductor, then you have a nonlinear harmonic oscillator, and then the energy level difference is different between 0, 1, 1, 2, 2, 3. And this is important. So why you need Josephson junctions? Because you need to introduce anharmonicity. This nonlinearity allows you to have a fingerprint or a frequency associated with 0, 1, which is different from 1, 2, and different from 2, 3, etc. And this is crucial for all these devices. You cannot just have capacitor and inductor, you need to have nonlinear inductors. So therefore now, the first giant atom is shown here. So there is the coupling a superconducting qubit to a surface acoustic waves through an IDT, interdigitated transducer. So let me just magnify this here because it's hard to see. So this is the schematic diagram, but the chip is here. So you magnify this here, you can get this picture, which is 5 microns. And you magnify it here, and this is 1 micron. And this is the interdigitated capacitor, which is like a capacitor where instead of being 2 plates, one on top of the other one, you have this kind of like this more surface between the different parts. So it's like a way to increase the capacitance. So let's make this bigger. And then, the length scales involved are L over lambda can go from 1 to 100. So they are much, much larger than anything done before. And this was done first at Chalmers by Gustafsson et al., Perdelsin, Göran Johansson, and to Fritz Koku. Did some beautiful work about a decade ago. And so you can see the atom as being like the source of sound propagating here, and this like the microphone. This is one way to see, although it can go both ways. So this is a magnified version here, and then this superconducting qubit is built to listen as well to see. See in the sense that you can excite the qubit via microwaves. But you can also excite it via surface acoustic waves via phonons. So therefore, the qubit can see electromagnetic waves, so it can see, but can also hear sound, but it cannot smell, it cannot touch, it cannot talk to you, at least not yet. We need to eventually couple to ChatGPT, might be able to talk to us, the qubit. So here it is. So therefore, in the future, there will be more experiments where quantized sound matter interaction will be probed instead of the usual quantum light matter interactions. So therefore, the typical study of light matter couplings is being replaced in some labs by quantized sound matter couplings. This giving rise to cavity quantum phonon dynamics instead of cavity QED. And we have actually some papers on this, which I will not describe today, or like in a separate talk on this, because so here it is, and then we go here. So this is a cartoon from Roscoe and Tahani in Science. So there is a classical quantum solid sound in A. An ultrasound imaging works by creating and detecting sound waves with piezoelectric crystals with this handheld wand. In B is a schematic of the superconducting device here that operates in the quantum regime at cryogenic temperature. So this is like 10, 20, 30 millikelvins, it's very low. The acoustic transducer is coupled to a superconducting qubit fabricated on a piezoelectric substrate. So the sound, when it propagates, is coupled to electric field. So the surface acoustic waves are shown to interact in a quantum way with the artificial atom. So therefore, this qubit couples strongly with surface acoustic waves, and then they did it on purpose on gallium arsenide piezoelectric crystal because the strain, the motion of the atoms, and the electric fields are directly coupled. So therefore, the electric fields provides a natural interaction with superconducting qubits. They then integrated this surface acoustic wave transducer into the qubit, which can act as both as a speaker and a microphone for the surface acoustic waves. So therefore, exactly, this is like a sound-sensitive superconducting qubit, and then on top of a gallium arsenide crystal. So therefore, the interdigitated transducer, analogous to the one shown in panel A, generates surface acoustic wave directed toward the sound-sensitive superconducting qubit. And then, but this IDT can also detect acoustic waves that reflect back from or are generated by the sound-sensitive qubit, which one might call a sound qubit. So therefore, the interdigitated transducer can translate the incoming sound wave to an electrical signal that can act as an input signal to the qubit. This qubit is designed to interact with phonons precisely the same frequency. The qubit can be used to probe the quantum nature of sound because the energy levels are not equally spaced. So this atom and the capacitor attached to it can actually generate sound or can receive sound, can be both a speaker and a microphone. Exactly, so the phonon can excite the atom, and then exactly when the sound wave is in resonance with the qubit, the phonon can be absorbed as a whole, and the qubit is excited from the ground state to the first excited state. If you try to send a second phonon with the same frequency, it cannot scatter until the first phonon is released. So the atom has to decay before being able to absorb another one with the same frequency because already has been excited. These experiments show this by continuously changing the rate of impinging phonons from a much lower to a much higher rate with respect to the qubit. So therefore, and then this is very similar to what happened with circuit QED, but doing the thing with sound. Also, they use microwave radiation to independently excite and dry the qubit without sound. And the excited atom relaxes to the ground state by emitting phonons that travel to and induce a characteristic signal at the interdigital transducer on the other side. The time of the phonon state to get to the other side differentiates the sound from purely electrical signal because the losses are well known. And then the crosstalk signals can be removed. So therefore, 40 nanoseconds later, the sound wave was detected, and this delay corresponds to the sound wave propagation time from the qubit to the detector. So therefore, there are acoustic and microwave drives were applied to find additional analogs of atomic physics, which were very interested on analogs. What can you do on the circuit that you could do with atomic physics, like, for instance, the outlier tone splitting related to the Stark effect and some other effects? We had a paper in collaboration with Peter Leak at Oxford and Anton Fritz Kokum and myself in Riken on circuit quantum acoustic dynamics with surface acoustic waves, where this interaction was studied in detail, but that's a separate talk because the system is somewhat different. But the idea is the same. You replace the light matter coupling studied for like 40 years or longer with sound matter couplings, that is quantized sound. So this will be cavity quantum phonodynamics instead of cavity QED. So this is a new, relatively new chapter in the past, 8 years or so. Okay, we talked about this already. Superconducting qubits are talking to each other via transmission lines. So you can have here, let's say, this transmission line is a way to confine the electromagnetic field. You can make this as long or as short as you want, coupling different qubits or different squids. And regarding the squid, okay, the coplanar waveguide confines microwaves to the chip, creating a 1D electromagnetic environment because the Z component, the width is negligible, the transverse one, negligible, everything would happen longitudinally. So it's really essentially a 1D electromagnetic environment. And there is a center conductor here and two ground planes, like a cross section of a coaxial cable. So you take a cable, you slice it on the left or the right, and this is the central part. And this is how it looks like. Now, regarding squids, this is for the non-experts in the audience. You have a superconductor with a barrier here. This would be the junction, the so-called Johnson junction, and there is a field penetrating it. And then the squid equals to two junctions. This is the DC squid in parallel, forming a loop. It behaves from the point of view of a circuit. It behaves like a flux tunable inductor. It's an nonlinear inductor. So this is the electrical circuit kind of analog. And people get confused because why it's called squid. Squid is superconducting quantum interference device, and it's not this type of squid because many people just, this is the one you see in a seafood market, but this is the squid used in experiment, which is this one here. So therefore, how to make this experimentally? So we're working on the theory, which I'll show you in a moment, but then the experiment was done by Will Oliver groups at MIT. They're still working on modified versions of this to do other kind of things, exciting experiment related to Bell inequalities, entanglement, things like this. But I'll show you in a moment. So therefore, the circuit is one here. So the blue part or purple one is the waveguide, connecting, so the photon comes here, interact with one atom, which is the yellow one, and then goes into this atom here, which is the yellow one here, and then to this one here back, and then here, and then get out. But you need to have the readouts in red attached to the qubits in yellow. And here you can see the photons interacting here. And with this length here, you can make the coupling to be stronger or weaker by having this length shorter or longer. And the green one is the flux lines to be able to tune the energy of the qubit to make it in resonance or off resonance with incoming photons. And so here is the photons are coming on, let's say, on the left, and you pump them here, and they go to the second dimension, go to the right. You can see, you can control the way they interact with the atoms. So this work was started in Chalmers by Anton Fritz Kokum, Per Delsin and his group, and then Jörg Johansson and his group. Eventually continued my group when Anton came to my group for about 4 years or longer, and also because other people involved, and then the experiment was done by Will Oliver and Dan Campbell and Cannon, beautiful experiments. And somewhat, I'll be talking about these experiments today, and these experiments, I will describe them some other time, because this is a very beautiful experiment that requires a separate. There are other people also involved, mostly like postdocs in my group, most of them, but not. So now what happens when you have a giant atom? So therefore, you can have, so in the normal case, the artificial atom has one coupling to the electromagnetic environment, which is its coplanar waveguide. In the giant atom, there are multiple coupling points given strong interference effects. So the coupling points will be X1, X2, X3, X4. This introduces additional time scales, which are the time travel across the atom, let's say xn minus x1, for instance, all this here, and also the time it takes to go from 1 to 2, and 2 to 3, and 3 to 4, etc. So we work in the limit where this time scale is negligible compared to this relaxation rate. How they interact? Interaction with the waveguide can be written like this. So the system, if the qubit is in the 0 state, it can go from 0 to 1 or 1 to 0, depending on these operators here. And this is the coupling G, so assume the coupling is the same, 1, 2, 3, 4. But at each point, there is here an X1, X2, X3, X4. So therefore, there will be different couplings depending if it is an X1, X2, X3, X4, and also here. And this is what controls the transition from 0 to 1 and 1 to 0. The relaxation rate, gamma, has this form here, and this is a way to couple with this is the environmental coupling is here, where the A is the sum, discrete Fourier transform, of the coupling strength and the actual location of the coupling. So therefore, this can describe a structured environment. So you can actually control how your atom is talking to the environment. So you not only can design the atom, but you can design how the atom is going to interact with the environment. So this is atomic physics with a level of control that atomic physics typically don't have. You can design some atomic transitions to couple strongly, while all transitions couple weakly to the environment. They call environmental engineering. So you decide how it talks to the environment. So in this case, we have equal coupling strengths, G1, G2, G3, G4, equal spacings between connection points, and then you can see what happens in different cases. Let's say the blue one, there are 3 n equal 3 couplings, and then at n equal 10, there are 10 couplings. You can have a sharper feature here. So you can have here a strong coupling, in this case would be a strong relaxation rate here, and here is a weak one. And in this case, there are 4 connection points, but then there are designs which involve for wide minima, like in the red curve. So in this case, there's a minima here for the relaxation rate 1 and 0. And here, wide maxima, like for the blue curve here, or multiple maxima, like the black curve, there's a maximum here. So depending on how you couple to the system, you can have either wide maxima, wide minima, multiple maxima, etc. So this is the idea. You're controlling not only the qubit, what has been done for the past 20 or some years, but also how interact with the environment. Now, what happens when you have multiple atoms here? So therefore, you can have 2 atoms here, but this is open waveguide left, right. This is semi-open. He is open here, and this is closed. And let us consider here purely open. So the photon enters from the left, leaves to the right. So you can have atom A and B separated. It will be like A coupling because atom A, B because atom B, braided A, B, and this one nested arrangement, ABBA, which is very suitable because these studies started in Sweden. So here we have A, B, A, and this is the nested arrangement. And then we just need to compare them, how these couplings interact, and to see which one can provide some advantage from the point of view of circuitry or atomic physics. Or we show that the giant atoms can be protected from decoherence through the waveguide, but still have exchange interactions mediated by the waveguide. Unlike in decoherence-free subspaces, here the entire multi-atom Hilbert space, which are 2 to the n states for n atoms, is protected from decoherence. This is not possible with small atoms. So these systems allow a degree of control that is simply impossible with the normal small atoms I've shown before, which are either superconducting or atomic or Rydberg atoms. Or we further show how this decoherence-free interaction can be designed in setup with multiple atoms and how to implement them. And also, this can be extended in the future to 1D chain of atom with nearest neighbor couplings, or a collection of atoms with all-to-all connectivity. We're already published with several groups, all-to-all connectivity, by looking at other problems. This is like a new, relatively new area over the past few years among superconducting qubits to have this high connectivity. So let's try to be more quantitative. You have a master equation here. So you have the density matrix evolves in time in a way that involves qubit A and qubit B. And this is the atom of the energy difference of qubit A and B. There's an exchange interaction. So therefore, the energy that decays in B is absorbed by A, and the one which is decaying in A is absorbed in B. So this exchange interaction between A and B, and the coupling is G. There is an individual relaxation because qubit A decays with a certain way. This is the dissipative part, and this is the individual for qubit B, and there is a collective relaxation involving both A and B. So this is the Lindbladian operator for the system here. So there is here a collective relaxation, individual one. If you choose the distance x1 minus x2 here for the standard atom, you can get no exchange interaction or maximal collective decay depending on how to on the value of phi here. You can get a dark state, subradiance, or superradiance, bright state. If you choose the right distance between them, phi, which would be maximal exchange interaction, no collective decay. So by changing, just even with small atoms, you can decide what states you're going to produce based on the distance between them. But right now with giant atoms, there are more possibilities, because you can vary these distances here and distance between atom A and atom B. So we're going to see what happened with all of these cases, C, D, E. So small atoms for mirrors, separate giant atoms, braided and nested. So we can look at the frequency shift, exchange interaction, individual decay, collective decay, and many results can be obtained analytically when you assume equal coupling and equal distance. If you decide to look at the more general case, you need to do numerically. It can be studied. But when you plot them, if you plot, let's say, the coupling G, for instance, let's consider the case ABAB. The coupling G is fairly non-zero. I mean, it's fairly strong over a wide range for this configuration here. When you look at the individual decay, which is this dashed red line here, near the origin here is pretty flat. So you can get zero individual decay and zero collective decay if you choose this configuration. So therefore, we decide to focus on this because the other ones we're not providing the goal, which is to bring the decay rates to 0, individual and collective, and to keep a strong coupling. So it's only this configuration A, B, A, B, which is one here, A, B, A, B, which is one nested here. So the braided setup is the only one that enables completely protected interaction. This is a nested one. So that's our focus based on these calculations. And then only in the case of braided giant it is possible to have the coupling non-zero when the individual relaxation rates are 0. So it's a decoherent free interaction. This can be understood as follows. The individual relaxation rate 0 implies that the phase acquired traveling between the connection points of each atom is an odd number, odd integer times pi. So you get destructive interference internally within the two legs of an atom. But the collective decay is about interference between emissions from connection point belonging to different atoms. But the sum of this contribution will be 0 when the emission from two connection points of one atom interfere destructively. So therefore, the collective decay, you need to focus on the distance between the atoms, and the will decay, the distance between the two legs of each atom. So this is the main idea. So you're playing with the interference pattern there. The exchange interaction is set by emission from connection points of one atom being absorbed at connection points of the other atom. So they're just talking to each other. They're exchanging energy. For separate and nested giant atom, the emission from two connection points will cancel. But in the case of braided ones, the two interconnection points are placed in between the other atoms. So the contribution of the two connection points of the other atoms, they do not interfere destructively necessarily. So therefore, and this can be done, we did for arbitrary Bayer relaxation rates at each connection point, arbitrary distances. So the parameters were varied to see how robust they were, and they were fairly robust. So therefore, now it's clear that the connection has to be a point x1 for atom A, x1 for atom B, x2 for atom A, and x2 for atom B. And this is represented schematically here. So here there is x1 for atom A, and then x1 for atom B, and x2 for atom A, and x2 for atom B. So this is the braided giant atoms. So the summary of this part is that the giant atom is coupled together at multiple points, separated by many wavelengths. And these multiple coupling points means interference effect which you can control. You can design frequency-dependent relaxation rates for a single giant atom. Two braided giant atoms can completely decouple their entire Hilbert space, not just a single dark state from the waveguide, but still have a strong exchange interaction mediated by the waveguide. And this is not possible with small atoms. So this is the main message of this work here. And then let's look at the experiments here. This beautiful work done at MIT. So there is a long meandering transition line, blue curve, creating this multiple wavelength between different coupling points. As you can see at the coupling here. So this is the qubit in yellow. The red one is the readout, and the flux lines are controlled by the green, so you can control the energy scale from each qubit, and the waveguide is in purple here, or blue. Here it is. Already talk about the readouts in red, control lines in green, qubit in yellow. So for a single giant atom, you need to do the following. This is a plot of T1. T1 is the average time the atom is excited before it decays. So these are the fits on the experimental data for qubit A at 3 different qubit frequencies. And then the relaxation rate is the inverse for qubit A as a function of the frequency. And you can see here there is like this minimum decoherence here. So decoherence free. I mean, it's not completely free, but it's close to free. This is very good decoherence. And then the qubit couples from the waveguide at this decoherence free frequency, which is like 4.6 something gigahertz, and a lifetime is some number of microseconds, and then which is 31. But then if you move away from it, and it goes like 1 order of magnitude smaller here. So therefore, what here has been done, you're exciting one qubit, monitoring through the resonator. So you are changing the relaxation rate by more than 1 order of magnitude, as you can see on top, and this can be derived analytically. But now the next step is you need to measure the exchange interaction strength between the qubits from avoid level crossings versus the qubit frequency, and the avoid level crossing is shown here. So this is the strength of the coupling. So you're probably the tuning, you're changing the parameters here. You see how they're talking to each other. But you keep one qubit at the initial decoherence free, which was 4.6 something. So the fit to theory, which is a solid line, is plotted with the data, red dots, and the coherent free frequency shown, which is the vertical dashed line. The qubit spectroscopy is indicates that this is the coherence free for one qubit. And then the applied drive is swept to plot the qubit frequency for multiple qubit detunings. And then even though the qubits are decoupled from spontaneous emission, there is an exchange interaction which is mediated by virtual photons and can be measured of the order of megahertz. So therefore, in this case, tuning both qubit frequencies in synchrony to define interaction strengths of resonance, and then you find a non-zero interaction at the frequency protected from relaxation into the waveguide. So it's a protected interaction. So this is the summary of the entire thing. We began with small and large atoms, and then we find that this one here is the ideal one. This experiment was done. And then, but there is also a design with 3 coupling qubits. So therefore, there is coupling 1, 2, 3, 1, 2. They're here unequal coupling because you can make this one here small, weak coupling, and this one here stronger because it's longer coupling here. You can get coupling 1, and then here, and then 2, and then 2 here, and then 3, and then 3 here, and then out. So this is a more complicated one. And then it is possible to do the measured and fit the single qubit relaxation rates are in blue. And the resonant interaction, exchange interaction strengths is shown in red for this configuration here. And then there are 2 decoherence-free frequencies, one for qubit 1, qubit 2. The coupling strength can be obtained, so the order of 1 to 5 gigahertz. And then, so therefore, these are 2 frequencies which are where the qubits are protected from relaxation, because the relaxation is essentially 0 at this point. So this enables turning the protected interaction on and off by detuning the qubit. So you start here with this qubit at the decoherent free time, the decoherent free frequency, and then you put them to interact. So they are both the coherence free subspace, and then you put the interact for, let's say, 170 nanoseconds, and then you pull them out, you see the readout. So they're essentially decoupled initially. This is a pi pulse to excite it, and they interact and then see readout. This allows to do something called the square root ISWAP gate, preparing this state with 94% fidelity. I mean, there are better ones now, but this was enough to do a universal gate set. This is the excitation versus time for qubit A and qubit B. So the time domain chevron patterns are shown here, demonstrating the exchange coupling between the qubits at the upper decoherence frequency as a function of the coherence time, and then and the qubit detuning. So this is the detuning here and the excitation, and you can see the qubits are exchanging energy back and forth between qubit A and qubit E. The excitation will swap maximally with this period, and when this delta is 0. And it's suppressed when delta increases. So this is a summary of the circuit, how the exchange energy is going between both of them. And this is allowing to do these ISWAP gates, which are here. So the ideal ones are slightly higher here and there. So this is a summary. So this is how to do waveguide quantum electrodynamics with superconducting artificial giant atoms. And then we also are studying how to do intuition from 2 atoms could be generalized to many, since the interactions are pairwise. So, and then the question is, well, where do you put the space for readout and control line? This is something that are details that are being explored right now in different projects. And so the sign and the amplitude of each nearest neighbor coupling can be designed separately. So it's like having a chain of spins, like an easy model, but you can put the coupling control. The sign could be positive or negative. You can ferromagnetic, the ferromagnetic coupling. You can strong, weak. You can design your favorite system. You have control over it. In this case, there are actually expressions of how to do this coupling accurately. Also, this is a sketch with 3 giant atoms. In this case, it's to do all 12 coupling, but there are ways to do it for more than 3 qubits. So in summary, we saw how these multiple couple points allow interference effects and how you can design frequency-dependent relaxation rate for a single giant atom. And among different configurations, we found that 2 braided giant atoms can completely decouple their entire Hilbert space, not just a single dark state, from the waveguide, and still have a strong exchange interaction mediated by the waveguide. And all of this is not possible with small atoms. Thanks for your attention.
Thank you, Franco, so much. Yes, questions. Nicola Bondarenko, please.
I think I took like 50 minutes, no? Because we started late. No?
Exactly. Very nice.
Yeah.
Thanks.
I have a question. Well, I was confused a bit, not only because of the capital squid versus squid, but also because the atoms which are not round and because qubits that have many energy levels. But anyway, my question is, you showed the experiment where there are many oscillations. Well, is it similar to Rabi oscillations?
These are exactly Rabi oscillations, namely the photon is absorbed and then the system is excited, and after a typical period of T1, then it decays and provides the photon to the other qubit. So they're exchanging interactions back and forth between qubit A and qubit B.
Well,
and
then my question will be the next. I was thinking about sort of James Cummins decoherence, and the situation is like that because you have the capabilities to suppress the decoherence. So in principle, I was thinking you could be able to repeat the James Cummins situation with quantum collapses and revivals when there is a collapse to not to zero, but to equal probability 1/2 between upper and lower occupation, and then a revival of the oscillation. Is it possible? How do you think? Because it was never really firmly established experimentally before.
Here, there are points in time where the probability of being on qubit A and B are equal, and then the probability to be on qubit B is larger and qubit A is 0. So there are times where, so this is essentially James Cummins model where the photon is being exchanged back and forth. The collapse and revival has not been studied in this system because it was not the goal, but in principle, it could be done. It's just a matter of manpower and time and focusing on this. But this is essentially Rabi oscillations. Now you can see here these chevron patterns here. It's this time domain show the exchange coupling the qubits, and then as a function of the interaction time, and then the excitation will swap maximally right in the middle. But when the detuning is larger, that is happening, but then it's suppressed very quickly. So therefore, this is happening all the time, but if you want to do it better is when the detuning is 0, but this is James Cummins.
Thank you very much. Thanks for the introduction to the subject.
Thanks.
Yes, Andrei, please.
Yeah, thank you for a very interesting talk. I would like to ask a question about generalization to many giant atoms. So, is it still possible to completely suppress the coherence when we go from 2 to 3, for example, or more? Or it's less strict than?
Will you if it is possible to talk slowly to the microphone, because the sound, it wasn't clear. So if you speak very slowly to the microphone, will be easier to follow. Sorry.
Sorry. Yes, my question is about a many atom case. When you go to 3 giant atoms coupled, can you suppress completely decoherence in this case as well, or not?
Oh, I see. Okay, this is a good point. Essentially, for the 3 atoms, we have not done the systematics or the decoherence. It is possible to do it pairwise. So therefore, it's possible to do it between A and B, and then B and C, and C and D. So in principle, it can be done with N of them, but it is done pairwise. So the proof is done by doing it like a pair by pair. And if you do it pair by pair in an N by N coupling, in principle, it'll be all talking to each other. And then, but then you want to have some of them detuned. So therefore, the energy goes from qubit, let's say 1 to 3, and then 3 to 7, but no other ones, the ones that are detuned. And then you detune 1 and 3, and you tune in resonance number 4 and 8. So therefore, the energy goes to 4 and 8 back and forth. So by doing this tuning, detuning, you can have pairwise interactions that will be decoherent-free interactions, but pairwise.
Thank you. And if I may, one more question about whether it's possible to go beyond 1D chain, but go to 2-dimensional geometry, for example, of the lattice with giant atoms.
It is possible to do the following here, like this 1D chain. An example is this one here, which are 3, and then the other one, imagine here to have 2 other ones, so this connected to 3, and this also to 3, so it will be like a Cayley tree, expanding in different directions. So there are different configurations that have been discussed by one of the postdocs looking at different of them, but we need to find some geometry that would be easier to do to our experimental friends. They found it easier for the moment to do this kind of 1D geometries, but in other experiments, the ones in China, we have worked on 16 qubits, and they can all talk to each other. But those ones are not giant atoms. Those ones are like, it's looking at different kind of problems. So it's the issue of connectivity is being addressed now by different groups for the past 4 or so years. There are more and more groups that can do multiple connection points into even up to the point of 16 qubit where all are connected to all.
Thank you.
Electortana, please.
Oh,
Your microphone, Oleg.
The microphone.
I'm sorry, I didn't see. I'd like to ask about maybe this question is close to the previous one, about the realization. Because if consider a giant atom as a squid loop, it should be large enough along the waveguide to be comparable with the wavelengths in this waveguide. But this means maybe large inductance. But if you think about this atom as a LC oscillator, you have energy spectrum in gigahertz domain. So how to solve this problem? Large enough loop and energy spectrum in gigahertz range.
In the initial giant atoms made in Chalmers, they had squid. In the more recent ones, we you see here, there is no squid. So you see the qubit in yellow here, and the length scales are about 150 microns here. I think it can be done smaller. And then I think the dimension was chosen to allow large coupling here because it's long, and here is a shorter coupling. So this is weak coupling, equal, and this is strong one. And there is no squid loop in this configuration. There is this green flux line that control essentially the energy level spacing. There's a readout in the back here. So there are no squid loops in the experiments that I discussed. They were in our collaboration with the MIT group, but the squids, they were on the previous ones. Because in that case, they were surface acoustic waves. The work we did also with the Oxford group, surface acoustic wave. In this kind of giant atom, there are no surface acoustic waves, and it's a different flavor of experiment and physics. So there are no squids here.
Thank you very much. Okay.
Now, Alexander, please.
Thank you. My question is rather general. Consider a piece of waveguide closed from one side and open from other side, and say lambda by 4. Can it be very generally named a giant atom because its size is comparable to the wavelengths, and we can, in case when we have a closed from one side waveguide, we can add multiple times lambda by 2, and then we have a very big compared to the wavelengths resonator. Can it be very generally named a giant atom?
The configuration you're describing is one side closed, one side open. There is some parts lambda over 2, some parts twice lambda. So it's not clear to me exactly how the geometry is, but in order to make a giant atom, you want the qubit to be touching the waveguide at points which are far apart, like in this case, the photon is coming here and is interacting with the atom here. But then there is this long, it's done on purpose long, to talk here, to interact here, and then it comes here, this even longer route, and then touches here, and then long again, touches here, then very long here, back here, very long, touches here, and then it's out. So each case needs to be seen in this context, like in a diagram, to see who's connected to who. But to do a giant atom is you need to have essentially very long distance between connection 1 and connection 1, connection 2 and connection 2. What other things that can be done are the following, like looking at bound states and looking at chiral states, and then looking at interference in the non-local coupling, and then it's a tunable chirality. So therefore, the idea is to do a chiral bound state that can induce directional dipole interactions. So therefore, this we think is experimentally implementable. But in this case, there is here a left bound state with a certain impedance, a right bound state with a different impedance. This is a coplanar waveguide. And then for each case, you need to draw the diagram. You need to see, you need to put capacitors, you need to put the junctions. And then this is a waveguide impedance with varying periodically in space, which enables bound states and creating the opportunity to break translational symmetry. And this was studied essentially by my postdoc. This is like a theory work on here. And looking at issues like chirality and tuning the the chirality of the bound state, because there are many people interested on how to study the chirality of bound states in these systems here, and also how these chiral bound states talk to each other. And then, so we're looking at the overlap between the states, determining the strength of a protected exchange between the atoms. Exactly, it's possible to realize something called the Schrieffer-Higger model, which is a very popular model for topological physics. And then the coupling direction can be switched by chain waveguide modulation. So therefore, we're able to look at how to couple giant atoms to adjust some photonic crystal waveguide. And there is a chirality in the bound state around the small atom can be controlled. And then we can implement these kind of models that people are interested to do experimentally. So we're extending this in different directions. And the configuration you described can be done, but there can be done many of them, but it requires putting the computer or studying analytically and see what happens where you put the connections, and then try to get results for different values of x minus, x plus, etc. So there are many, many different possibilities, including the one you described and many other ones. But the devil is in the details. For each case, you need to look at the details and how things work.
Thank you. Thank you very much.
So to summarize the response, to have giant atoms, you need to have bound waveguides to touch in several points. Is that correct, Franco? And you partly addressed what's the chiral quantum optics. Can you say about this? I mean, there are different quantum electrodynamics, waveguide QED, circuit QED, and now we can learn about chiral QED, right?
Some of these bound states have a certain chirality, and this can be essentially measured. So we were predicting how experiments could identify these bound states and their chirality, and then also to extend the problem into chains like the SSH model involves two kinds of coupling. Let's say coupling 1, 2, 1, 2, 1, 2, 1, 2. And then there is something called a dimerized state, non-dimerized state, and then there are some topological features there that people find interesting in these models. So there are different possibilities, but I'm showing you a few of them, but there are other ones which we're also exploring now.
Also, I wanted to ask you about quantum simulation. You started from this. Which advantage you'd have with giant atoms instead of regular atoms coupled in single points?
One way to think about quantum simulation is the following. Let me see this one here. It's, sorry, let me go like this. Is chiral bound state is here. The Schrieffer-Higger model was initially proposed to study transport in 1D chains, especially in one called polyacetylene. And then it has some bound state, it had some fractional charge, this is a normalized charge. It had something called the Paradox instability, which is a gap at the Fermi surface due to electron-photon coupling. But it's not so easy to study some of the topological properties of this model experimentally. So people are saying, can we map the model, which is interesting theoretically, into something which is more controllable? Because polyacetylene as a polymer is not easy. So here the goal is to emulate or simulate the SSH model, which was proposed to study X, but modeling with another one. So this is like an analog emulator or simulator. And this can be done because the couplings can be determined, the interaction energy A decays, B absorbs the energy, B decays, A absorbs the energy, and so this is an example of a quantum emulator or quantum simulator, or how to emulate an atom coupled to a waveguide, but instead of being a standard photonic crystal waveguide, it's a Josephson photonic crystal waveguide. So all of this is clearly like a superconducting analog of an optical system. And the photonic crystal waveguide has been replaced by the Josephson one. And so all of these are quantum simulations. Even from the very beginning, it's the first one here was replacing the traditional atom, let's say like last century, the atom they look like this with this atom here, but instead of interacting them via electromagnetic interaction, you simply create your atom as you wish. You can design the transition energies, you can design how they talk to each other, and then how strong, because you can put this length strong or weak, I mean, short or long. So all of this is like designer atomic physics or designer quantum optics. In the ideal world, imagine a company that sells you an equipment and you say, I want to have atoms of this type, tac, tac, and you input on the iPad there, and I wanted to interact with this, and then automatically appears the chip outside and then do experiment for you. Ideally would be, because these are becoming more and more automatized. There are more and more groups essentially jumping into this and doing all kinds of new forms of atomic physics, new form of quantum optics, and also new form, what they call them, quantum microelectronics. And also they're looking at the light matter coupling. And so it's like a different way to do electronics than before.
Many thanks, Franco. More questions from the audience? And since it seems not to be the case, Franco, thank you so much for joining our seminar, for the insightful talk. Very interesting and beautiful lecture.
You're welcome. Thank you for the invitation, and thanks.
Thanks.
So therefore,
good luck to everybody.
Okay. Thank you. Okay.
Bye-bye.
Bye-bye.
Very much. Bye-bye.
Okay. Bye-bye. So I'm going to go here. Let me go into the Zoom here.